We're given a string and we need to count how many palindromic substrings it contains. Now, a palindrome is a string that reads the same forward and backward. A substring is simply a contiguous part of a string. For example, consider this word. There are 9 palindromic substrings. A single character by itself is also a palindrome. So how do we count all the palindromic substrings? The most straightforward approach would be to generate every possible substring and then check whether each one is a palindrome. Generating all possible substrings takes O of n squared time, and checking each substring can take another O of n. So overall, this approach takes O of n cubed time. But can we improve the time complexity? Let's examine how palindromes actually form. If a palindrome has an odd length, the center is the middle character. One way to find palindromes is to place 2 pointers at the center and expand outward while the characters match. For an even length palindrome, there is no single middle character. Instead, the center lies between the 2 middle characters. So we place the left pointer at one middle character, the right pointer at the next one, and again expand outward while the characters match. And from this, we get the key property we need. A palindrome is symmetric around its center. That is the idea we'll use to build our algorithm. Now let's look at this string BBBAB. Instead of brute forcing every substring, we treat every index as a potential center and expand outward. Suppose we are processing index 1, the second B. For the odd length case, we start with left equals 1 and right equals 1. The single B is a palindrome, so we count it. Now we expand outward. Left moves to 0 and right moves to 2. The characters still match, giving us BBB. So we count another palindrome. If we try to expand one more time, left moves outside the string, so we stop. Now let's look at the even length case. We are still processing index 1, but this time the center lies between 2 characters. So we start with left equals 1 and right equals 2. Both characters are B, giving us BB, so we count another palindrome. We expand outward again to indices 0 and 3, but this time the characters don't match, so we stop. Expanding around index 1 gives us a total count of 3 palindromes. In our final algorithm, we will do these odd and even expansions for every index in the string, stopping only when we hit a mismatch or the boundary. Moving from checking every possible substring to expanding from the center drastically reduces redundant work. By doing this, we improve our time complexity from O of n cubed down to O of n squared. And here is the code. We keep a running count of all the palindromic substrings we find. For every index, we expand twice, once for the odd length case and once for the even length case.